Well, thank you guys for coming. As Mr. Dersh mentioned, my name is Katrina Tunis. I attended school here for 2 years, my first 2 years, as well as some high school dual enrollment. And I'm now at Grand Valley in my last year, gonna get a bachelor's of mathematics, very excited. And I am also looking at grad school, which is also very exciting. This research experience played a lot into that decision, and I'll talk more about that later. But I also want to mention that this was mentored research. My mentor was unfortunately not able to be here because she's giving a test to a bunch of Calc 1 students. But she was extremely instrumental in me really understanding and wanting to get my hands into math and continue down that field. So let's get started. All right, so brief outline of what I'm going to look at. First, we'll talk a little bit about why I wanted to do undergraduate research, then some background on RNA, before we dive into the actual math, which consists of my research interest, the research itself, and some future work. All right, so why undergraduate research? I knew going into this that math research was different from math in the classroom, but I didn't really know how different until I got started, and it is a world of difference. There is very little similarities between doing math in a classroom where you have somebody who clearly knows the answer and you have a clearly laid out path of how to do it, and sitting down with a sketchbook, which is what I used, and this problem that you don't know if it has an answer, you don't know if anybody else has ever tried this, and you have no idea how to approach it. But overall, it was an extremely wonderful experience. I did many wonderful things with the research, learned many things, got very excited about math and about grad school. And then I did, as Mr. Dersh mentioned, have the chance to go talk at a couple other conferences, one at the Nationwide Math Conference in Denver, which was extremely interesting and a lot of fun. Another reason why I wanted to do undergraduate research was I was on the fence originally about whether I wanted to go to grad school or not. I knew I liked teaching, but I didn't know if I was really going to like research. So when I went into this, I was keeping that in mind, keeping that in the back of my head. Am I really going to enjoy this? And without a doubt, I am now more than confident that I definitely want to go into research in one way or another in grad school. And like I said before, it was just an overall wonderful experience. And I want to encourage you, if you're at all in any way thinking about going into math in the future, or you have some interest in math, check out undergraduate math research. My research was through my university, Grand Valley, but there are REUs, research experience for undergrads, that are across the nation. You go online and you apply for these, and you could end up going across the country to stay at this university, doing research with a bunch of other mathematicians that are in undergrad from all across the country, doing really fun things and learning about math. And it's a really wonderful experience. And if you have the chance, please take it. And if you have any questions, I work downstairs in the Math Prep and Learning Lab every night. So come ask me questions. I'd be more than willing to talk you into doing this. All right, so RNA, a little bit of background of what RNA is. I'm gonna kind of compare it to DNA because that's something we're a little more familiar with. But I also want to prepare you. The way math research works is it sees a pattern in nature and says, oh, I really like that pattern. Let me represent it with mathematical models. And we just ditch the real thing altogether. So while we're going to talk about RNA for a little bit here, we're looking at rules that we can copy and follow. We're not necessarily looking to embody all of RNA in this math. All right, so DNA. We're all very familiar with this. It's got 4 nucleotides, adenine, cytosine, guanine, and thymine. They form 2 bonding pairs. Cytosine always bonds with guanine, adenine with thymine, no other combinations. It also has that very famous double helix that twists around in a circle. Welcome, come on in. We've all seen pictures of this. We're very familiar with that concept. And because of this double helix, actually, DNA is very strong and sturdy. You can bend it around and it won't break. RNA, on the other hand, also has 4 nucleotides, You'll notice a difference here. We have uracil instead of thymine, but still 4 nucleotides, 2 bonding pairs. But then it only has a single helix, which makes it rather weak and vulnerable to being damaged in some ways. So it likes to fold back on itself to form that double helix that RNA or that DNA has, making it much stronger and more sturdy, thus giving us the property that I looked at all summer. All right, so one way to represent the folding of RNA is with what we call non-crossing matchings. This is the idea that one nucleotide can bond with another as long as that bond doesn't cross over an already existing bond, like you see here. This is a valid non-crossing matching. This is not a valid non-crossing matching. If you want to take your fingers for a moment, imagine these 2 are nucleotides and these 2 are nucleotides, and try to form that bonding right there where they cross over each other. You, like, wrap your fingers around. You notice that it doesn't work very well to try to cross them over each other, versus where they don't cross, you can just kind of pull them together and it works really nicely. So you see, this idea doesn't work in real life. Therefore, we're not going to represent it in our model. Another way that we can represent the folding of RNA is folding around a graph tree. You'll see at the top we have the same word written twice with 2 different foldings on it, represented by the non-crossing matching. If you just want to represent taking this word and stretching it out, we can then wrap it around this tree so that the 2 sides of the edges have nucleotides that are bonded together. That is how you would represent it with the folding tree, or the graph tree. I did not use this model so much because it didn't work as easily with my computations. However, it is a nice visual representation of this is what we're working with. All right, so now, making that slow transition into the math world, we're going to take some rules away from RNA that is going to represent our mathematical model. First of all, I'm not going to call them strings of RNA. I'm going to call them words. And the words are made up of letters that have the characteristics of RNA. Next, instead of using 4 nucleotides, I reduced the problem down to just 2. 2 letters, called them A and B. This will create a platform which I can build off of later, if I get around to it. I did not get to that this time, so all of this research is represented with just the 2 letters. The next thing is a letter can only bond with 1 complement at a time. You're not going to see 3 nucleotides bonded together in real life, so we don't want that here. Another thing is I wanted to only think about foldings as pairings of all of the letters in nucleotides, all of the letters. I didn't want any letters left over. 1, this greatly simplifies the problem. 2, it creates a hard line that this is folded, this is not. Along with that comes the idea that all the words must contain the same number of letters and complements. So a letter, I usually refer to A as the letter. Its complement is the letter that bonds with it. So A and B are complements. All right, so these are the rules that I worked with all summer. There are other things that you can go to RNA and you can pull out of them. Oh, what about this? What about that? But I started here. It gave me a nice, simple foundation to start on. All right, so going into the research, I wasn't really sure how to get started. I was all hyped up and excited and like, I'm ready to get started in this. We had talked about addressing this question, which we'll talk about in a minute, but my mentor was wise enough to say, let's slow down just a little bit. And she gave me some examples to work with first. And one of them is this idea where I had to find 6 different strings of length 10. So they had 5 A's and 5 B's, and they had to fold 0, 1, all the way up through 5 different ways. And this I think is in the wrong order. Crap. You know what? Anyway, we'll just go with it. So I worked with these ideas, trying to be as excited and creative as I could, and I realized that I just needed to slow down and work with the problems. I'm sorry. I'm a little flustered. I'm gonna take a moment. Okay, so the question that we were looking at all summer was, how many different ways can RNA fold? Given a string of length 2n, for any natural number n, what are the possible values k, we call them k values, or the foldability of the word, such that this word w will fold that many times? So what I was essentially looking for was, given this string I know has this length, I want to be able to list all the possible values that this word could fold. So I looked at that in two different ways. One was, how does k depend on n? So given the number, can I compute the number of different ways? The other was, how do words with the same length and the same k relate to each other? So can I find ways to go back and forth between them? So let's look at some examples of what this looks like. Over here I have the different lengths. Notice that they're even numbers because we have to have the same number of letters and letters and complements. I also have an example of what that word would look like. And then all of the possible words. And then the possible k values. So starting here with 2, there are 2 possible. It's A, B, and BA. Both of those can only fold one way, so all the possible values for k are 1. If you jump down here to 6, though, there are 20 different options. But even though there are 20 different options, they can only fold in these 3 possible ways. You will never find a string of length 6 that will fold 3 or 4 ways, which I thought was kind of bizarre, but was what I was looking for. I'm looking for these gaps. All right. Yes, so this is, I'm sorry about the misplacement of my slides, but my first question was these 10 strings, or these 6 strings of length 10. I needed to find strings that folded 0 up through 5 different ways. And I was very easily able to find the strings that folded 1, 2, 3, all the way up for 5 ways, but I could not find a string that folded 0 ways. I tried and I tried and I tried, and it was not working. I finally asked myself, can a word be unfoldable? And the short answer is, no, it cannot. I was able to actually show that given any word, if you have the same number of letters and complements, and you only have one of each type, then the word is guaranteed to fold every time. Let's kind of walk through an example, kind of proof by example, how this works. So given this theoretical string of a bunch of different A's and B's, the easiest thing to do is just go ahead and bond the ones that are right next to each other. I called those adjacent pairs. So there you go. Those are right next to each other, so they're bonded. Those are right next to each other, so they're bonded all the way across. Now it turns out that because these letters are right next to each other, it is impossible for any of the bonds we create later to cross over these. So we can, in a sense, act as if they're not even there and take them out. But then by taking them out, we form new adjacent pairs that we can bond. And you continue on in this manner until the entire word is bonded. And I obviously proved this more formally, but it showed that any word that has one letter and one complement and the same number of each is guaranteed to fold. This was a really cool experience for me because it was a little bit of a struggle with a little bit of a victory right away at the beginning to kind of give me a taste of how this would go. It also gave me some encouragement when I reached those problems where it was like, I have no idea how to approach this. So then, before I get into more formally the bigger things that I showed, let's take a moment to look at the people who came before me. The first thing I want you to notice as I go through this is that this is really recent research. The first paper published on this idea was published last year. So there was a lot out there for me to find and a lot of low-hanging fruit, which was really nice, but also a lot of room to just move around and kind of do whatever I wanted. All right, so the first paper was published by Black, Drelick, and Tomosko, again, you'll notice last year. And they showed throughout this paper, but also significantly in this theorem, that the amount of times RNA can fold, so the K values, is strongly dependent on the Catalan numbers, which, if you don't know what the Catalan numbers, which, like me, I did not, it's this right here, this somewhat complicated looking equation. And as you notice, the numbers get really big really fast. So it seems really weird that these folding numbers would have such a reliance on this, but they do. And one of the coolest way that is in this theorem, they showed that the largest number of times a string of length 2n can fold is Cn times, the nth Catalan number. But if it's not Cn, then the largest number of times is Cn minus 1. You will never find a K value between Cn and Cn minus 1. It just doesn't exist. Unfortunately, that pattern doesn't continue all the way down. That would just be way too easy. But again, throughout all of the possible K values, there's a strong reliance on the Catalan numbers. So the next paper was actually published by my mentor, Dr. Lauren Keogh, and as you can see, like 8 other people. They were at a conference, heard about this idea, and decided to work on it together. They continued proving that there's a strong reliance on the Catalan numbers, but they also showed that given a string of length 2n, you can find K values that are 0 up through n. Those are guaranteed to be there. Of course, going along with what I showed earlier, 0 is only valid if you don't have the same number of letters and nucleotides. Otherwise, 0 is not possible. So then, when I approached this problem, I actually built mostly off of this theorem. And the first thing I tried to do was I tried to add to that list. I was looking for that n plus 1. And it took me a long time to try to find it. And what I eventually ended up finding was that for all n greater than 5, where n is not 1 less than a prime number, there does exist this n plus 1. I don't know about you, but this prime thing right here kind of bothered me. So why can't n be 1 less than a prime number? And I'm going to go through a quick sketch of this proof, try to figure out why. So the way I approached this, my big picture idea, was I took 2 strings. Here I called them Q and R, and I let their length be twice as much as how many times they fold. So they fold y times, but have a length of 2y. I then found a way to concatenate them into a word that looks like this, such that their lengths added, but their foldabilities multiplied. If you're unfamiliar with this notation, this means that there are ZAs right next to each other. Imagine multiplication, except not actually multiplying. Right. So once I showed this, I was able to show that there exists a Z such that x plus y plus z equals n, and xy equals n plus 1 when n is greater than 5. Now, after I finally proved this, I was able to focus in on what is wrong with primes. And if you notice on the last page, I built the foldability of these words right here off of multiplication. So that immediately lost all hope for primes in my proof right here in this theorem. But I wanted to continue looking. Can I find a way to build a string that folds n plus 1 times, where n is a prime number, 1 less than a prime number? Or can I find a string that folds a prime number of times, to simplify that down a little bit? And it turns out it's still very, very hard. And that it has to do with the connection to the Catalan numbers. So the way you build K, the way you build the foldability of a word, is through 3 different things. The first is just the straight Catalan number. You take this word right here, has a K of C4, which is 14. And you can find a string like this for all the possible Catalan numbers. The next way, or the reason why this makes it hard to find a prime number is because LT Peabody showed that for all n is greater than 3, Cn is not prime, meaning the only prime Catalan numbers are 2 and 5. So not a wide variety of options there looking for prime numbers. So then the other option is multiplication of Catalan numbers. This again takes out the opportunity to build primes, because if we had just 1 times the number, we would be back up here with the issue of Catalan numbers, which are rarely prime. Example of this word right here has a k of C2 times C2, which is 4. The last way to build the foldability of a string or a word is the addition of Catalan numbers. And you'll notice here, we got another prime number added to our list. Because C2 is 2 and C3 is 5, 2 plus 5 is 7, that gave us a prime number. However, we still have difficulty finding primes, because the only way to add Catalan numbers to equal a possible folding of a word is if they are adjacent. And the large majority of Catalan numbers are even. So as I was continuing to look through this, I found again and again and again that it was very, very difficult to find a string that folded a prime number of ways, which was slightly discouraging, but also really cool at the same time, that primes can be so different from other numbers. All right, so after I reached this point, I kind of took a step back, and I started wanting to think about words that have the same foldability. So if I have this word here, can I make it into another word that has the same foldability? And I started messing with these ideas, and I had lists and lists of hundreds of different words, searching through them, trying to find patterns. And I was actually able to find some really cool things, which I called isometries. So an isometry is an operation on a word that doesn't change the length or the foldability of it. So they'll have the same k values. The isometries I found, I called reversal, cyclic shift, inverse, and reversible pair. So we'll take these one at a time. So reversal of a word is that word written backwards. If you want a more formal definition, I can give it to you, but it's daunting to look at and kind of hurts your eyes. So an example of this, you just take this word and you write it backwards. This gives us a completely different word that is guaranteed to have the same foldability because we didn't change anything about the letters. Same order, same number, same everything. Cyclic shift. This one I thought was really, really cool, because if you take this word, it's capitalizing on the fact that the first letter and the last letter act as if they are right next to each other. This word doesn't know that the first A and the last B are not right next to each other. So you can write it in this circle form and then rotate it as many times as you want, open it up, and have a completely new word that folds exactly the same number of times. This also relates really well to graph theory, if you want to think of these letters as vertices, or you can think of chords across a circle. I did not have a chance to fully look into those, but I am hoping to in the future. Inverse, this one capitalizes on the idea that A's and B's are, in a sense, identical. I can take this word, and because these A's don't act any different from these B's, I can just swap their position. So you notice the pattern 3, 2, 1, 2 is still maintained, 3, 2, 1, 2, except the roles of the A's and B's are switched. The last one, reversible pair, is one that I still don't fully understand, but I'm seeing over and over and over again. In some very specific cases, it is possible to have a word where you have an adjacent pair like this, sitting next to each other, and then you can flip it, and it doesn't do anything to the foldability of the word. There are also cases where you can have 4 letters where they just kind of swap orders, and it doesn't change anything. I, again, did not have a chance to look into that, but really cool in the way that it just doesn't care what order it's in. Now, overall, what makes these isometries really cool is this idea that I can take 3 words that have length 6. They all have different foldabilities, all different k values. You'll notice, if you remember on the slide earlier, the only possible ways to fold a string of length 6 was 1, 2, or 5 different ways. Well, it actually turns out that using those 4 isometries that I named, I can take these 3 words and create all 20 words of length 6, much like basis vectors can build an entire space, or other things like that. I also did the same thing to the words of length 8. I found 6 of them, all with different foldabilities, and again, all of the possible foldabilities for strings of length 8. And by doing these operations, I'm able to create all 72 strings that have that length. So future work going forward, I really want to go back to the issue with prime numbers, and I want to see if I can find a way to find those few prime numbers in there. I also want to go back, and like I talked about earlier, how cyclic shift creates that circle, relates to graph theory or circles. And I would like to go back and revisit that, work on it a little bit more, as well as try to find more operations, because I know that there are more. Thank you for your time.
Can you go back to slide 19?
19?
Okay, now, I wanted my frame of mind to be correct before I ask the question, so run through that again real quick.
Okay, so I treated these like members of a basis, and I used my operations on these to build all of the possible values that would fit under this category.
So for words of length 6, you have those 3, those are like you said, like basis vectors, and you can create how many from that?
20.
And then the next one, words of length 8.
I believe there are 72.
Okay. So, and then you had something about, what we're going to generalize on. So I look at that and I think, well, you got to generalize that.
I tried to, and I wanted to so badly, but I ran out of time.
No, yeah. Why don't you have that done now?
Well, it was so frustrating.
So what I'm wondering is that something that you consider doing? Is it something you're going to maybe consider pursuing? Is that right there just really fascinates me?
Yes. When I had on the future slides finding more operations, that would involve generalizing it. So I went and looked at the strings of length 10. There were 500 or something like that.
Yeah. Well, the number grows real fast.
Yeah. And I was able to find the operations that I had, but then when I pulled those out, I still had strings of the same foldability that I couldn't relate with those operations. So if I get a chance to go back to this, I would like to find more of those operations and then try to find a way to generalize it.
You've definitely hit on something that has an awful lot of questions on it.
Yeah. Also learned very, very quickly that math research is never finished.
Well,
which was probably the most frustrating thing for me to try to learn.
Well, the pursuit of knowledge never ends, and one must get used to that. That's very cool. Other questions?
Yeah.
So you had some of the theorems mentioned from earlier studies, but is there any definite formula that you came up with that can determine the foldability, or is that still
It's still an open question.
Yeah.
Right now we're just trying to find the possible values because nobody's really looked into. I looked at a little bit of, can I create these three or four letters mean that I have to add this number or subtract that number, and there just really doesn't seem to be anything like that because there's only so many possible combinations you can have, yet the possible foldings get I don't know about exponentially, but much, much bigger very quickly.
Sure.
Does that answer your question?
For sure.
in the back.
I was actually curious what made your research team look into this in the first place. Do you know?
Yes. Well, so it was just me and my mentor. And like I mentioned earlier, my mentor she's actually working on getting her paper published for this topic. And honestly, I walked into her office and said, I want to do undergraduate research. How do I do this? And she handed me a piece of paper and said, pick a topic. So I chose this one. I don't know why. It just looked interesting.
Yeah, it seems like it.
Yeah. Yes.
Is there a theorem out there with like your name on it, like in parentheses? Anybody else know? Or?
I did not put my paper up for publication, so no.
He's basically asking if you're famous.
No, no. So you can find the paper if you really want to go looking for it. It's on ScholarWorks, open source, but don't go looking for it because it's a pain to read.
Now, maybe I missed this at the very beginning, so I apologize if this is an inappropriate question because you've already answered it. But so I did invite people from the biology community here, and I don't really see too many of them in here. From a biologist's point of view, what's the significance of foldability?
I did not address that. Or you mean like why it's significant that RNA folds, or why is it significant that this research is being done?
I guess maybe both, because I know essentially nothing about RNA.
So the significance for for the fact that RNA folds is the fact that it makes it stronger.
Okay.
RNA with that single helix, it's very weak, it's very susceptible to being damaged. So when it folds back in on itself, it gains the sturdiness that DNA has with that double helix. With regards to my research, it has absolutely no significance on the biological community because it was mainly focused on pure math ideas. Maybe somebody will come along later and say, oh, I recognize
That's
this.
what we were talking about before your
Yeah.
talk, where the mathematicians do the math because they enjoy it.
Yeah,
And then
'cause they're
later
curious.
Someone comes along and says, this is useful. Okay.
Yeah.
All right. Thank you.
Yeah.
Could you give us some reference to the published papers, by chance?
Yes. I did not put it in the talk because I couldn't get LaTeX to work with me, but I can give you those papers when my computer boots up. I'll get that to you by the end. Are there any other questions?
So you see this as something that you're going to continue working on?
Yes. I don't know that I would write my dissertation on it, but I can definitely see myself down the road picking it back up and wanting to go back to it.
It's captured you.
Yes. It was an absolutely wonderful experience to be able to do this research, and it was just so cool to have my hands in something that was so new that there was so much out there to be discovered.
Very cool. Well, thank you so much for doing this, Katrina. It was very good. If anyone else has any other questions, I'm sure that she'll be happy to handle.